I guess we can start right on time. So welcome everybody to the first members colloquium of the new year. And it's a pleasure to have Ramon Van Handel, and he's going to talk about the Alexandrov-Fenchel Inequality.
Yeah, thank you very much. So pleasure to be here all year. It's been wonderful, and it will keep being wonderful. So I want to talk about this subject, which I've worked on for quite a number of years. And I gave mathematical conversations in the first semester about more about the history of this subject. So I apologize, those of you who were there, maybe there'll be a little bit of overlap in the beginning. But I wanted to focus on some results that we achieved in this a few years ago, and you know, other questions that come out of this. And I hope they will be for the audience, for people in the special year. So let's start with the most basic object that this talk is about, which is the convex set. Is a convex set, right? So it's just a set where if I take 2 points in the set, the line segment is also in the set. And it's a very kind of innocuous definition. So if you've seen it for the first time, which you have, of course, could be a little bit surprising that this object appears throughout basically all of mathematics. Right? It plays a fundamental role in mathematics. And I don't think that was obvious in the beginning of this subject, and it was the Hermann Minkowski. I think, you know, convex sets were studied in the 1800s before that for their own sake. I think it was really Hermann Minkowski who discovered the importance of convexity as a fundamental principle in mathematics. He was working on number theory, and he was working on classical questions of quadratic forms in number theory that were usually studied by arithmetic means. And he discovered that by just thinking about this geometrically, right? So you have a quadratic form, you look, where's the quadratic form less than 1? Well, that's an ellipse. And just thinking geometrically about these objects, he could prove very deep theorems in number theory. And pushing that forward, he discovered that actually the only thing that was needed is convexity. So I talked a lot more about this in the fall. Let me not dwell on it here. So Minkowski discovered this, the importance of convexity, and he decided that this was something that was worth studying in its own right. And in 1903, he published a kind of fundamental paper where he put down the basic theory of volumes of convex bodies. And it's an absolutely amazing paper. Unfortunately, it's in German. I don't believe it's been translated. But if you go look in this paper, you will find you will find all kinds of mathematics that has played an important role in the 20th century has its origins in this paper, right? So the theory of convex bodies. So this paper puts down the foundations of convex geometry, right? So anytime you use convexity, you're probably using some notions from this paper, and the notion of support functions, very basic things that appear in convex geometry come from this paper. Another thing you see in this paper is one of the very first stability inequalities for a geometric inequality. We have leading experts in this room who work on this topic, but you find one right in this 1903 paper. The very first paper has a stability of the isoperimetric inequality for convex bodies. The Minkowski existence and uniqueness problems, they played an important role in the theory of nonlinear PDEs in the 20th century, right? So they come from this paper. And as I will show you, the fundamental ideas about lock concavity also appear for the first time. So now at the same time, so this paper from 1903 contains some kind of open problems, or it motivates some open problems. And in full generality, some of these problems remain open to this day. So I want to talk in this talk about one of those open problems and tell you what we could prove in the last few years about these questions. So that little background, let me start by introducing the basic objects in Minkowski's theory. So let K1 to Km be convex bodies. The convex body is just a compact convex set. Okay? And I should tell you at the beginning that Minkowski's paper only works in dimension 3. Now, that was kind of tradition at the time. I would work straight in Rn in this talk. The basic observation of Minkowski is that you can do the following. Say that we take the volume of some combination, linear combination of these sets. So lambda 1 through lambda m are non-negative, let's say positive constants, right? So this is just a set. You pick a point x1 from k1, x2 from k2 until xn from kn. You take their combination, lambda 1 x1 plus lambda 2 x2, right? If you take all the choices of x1 to xm, you will get this. So if I take a linear combination of convex sets, now this is again a convex set. That's an easy exercise. And what Minkowski noticed is that this thing is actually a polynomial, which is an elementary fact, but it's not entirely obvious. It's a homogeneous polynomial of degree n. So here are the monomials. And then it has some coefficients. And these coefficients are called mixed volumes. So these mixed volumes are the coefficients of volume when viewed as a polynomial. As a function of
index it by I or something, right?
I beg your pardon?
You want to index this V by I or something? Or...
No. So the V is indexed by a choice of n convex bodies. Right? So I took, right? I have here m convex bodies. It's a homogeneous polynomial of degree n. So V takes as input n.
But where does I1 and In come?
I'm summing over them.
V doesn't depend on I1 to In?
V is a functional of n convex bodies. So you should think of this as analogous to the following formula. Lambda 1 f1 plus lambda m fm to the power n equals from I is 1 to I1 to In, 1 to m, lambda I1 to In, right? And then we get fi1 to fn. Okay, so these products are just a mix. Is it okay? So a mixed volume, the mixed volumes are functionals of n in dimension n, they're functions of n complex volume bodies, and more or less obviously by the definition, they're additive in each of the variables. What should not be obvious to you from the definition is that they're also non-negative. That's not an obvious statement. So these not only are polynomials, but they're polynomials with non-negative coefficients. And it turns out that these coefficients, they have all sorts of natural geometric quantities are examples of these coefficients. So you know many of them, right? So for example, volume is a special case. Surface area. Mean width. So mean width, right? I take a body, fix a direction, just look at the width of the body in that direction, just put two planes and measure the width. Average over all directions, you get the mean width. And many, many more natural geometric quantities are special cases of these coefficients. So, Minkowski realized, once you realize that volume is a polynomial and you have these non-negative geometric quantities that naturally arise, the natural thing that you think about is, well, now if we want to do geometry, right, we should think about whether there are natural inequalities that hold between these coefficients. And that turns out to be true. And the kind of most important inequalities area, you would think it would be called the Minkowski inequality, but it's called the Alexandrov-Fenchel inequality. This inequality has a kind of complicated history. So it actually appears in Minkowski's paper in 1903 in dimension 3. So the three-dimensional case of this inequality is due to Minkowski. And Alexandrov proved it in dimension n in 1937. What Fenchel did is not quite clear. So Fenchel has a Colloquium note where he announces a proof of this inequality. And there was no paper ever. And I tried to read this note and I couldn't make any sense of it whatsoever. So it seems likely that it should really be called the Minkowski-Alexandrov inequality or something. But anyway, so what does this inequality say? So take the mixed volume now of n bodies in Rn. And you see in the notation, I've already distinguished between these last n minus 2 bodies and these first 2 bodies. So this is an inequality where I'm going to vary the first 2 bodies and I'm going to fix the other ones. That's going to be important later on. And the inequality says that this is lower bounded by the same thing where I just replace KL by KK and L. This is the Alexandrov-Fenchel inequality, and it says, roughly speaking, that the coefficients of the volume polynomial are log concave. That's the statement. And the question, which appears in the very earliest papers on the subject, so this is the question due to Minkowski, Alexandrov, let's say. So in the 1903 paper, in the original paper of Alexandrov, this question appears, is when is there equality? And kind of surprisingly, this question remains open. So it's been, what has it been, more than 120 years? In full generality, the question remains open. However, we're a little bit closer now than we were. So let me try to give an example to explain how you should think about this. So this example is due to Minkowski. And so now we work in dimension 3. Well, let's work in dimension 3. So let's say be a convex body. And I'm going to take throughout the stuff what we're going to call B the Euclidean in any dimension, in this case in dimension 3. So there's a special case of this inequality which reads as follows. If I take VB KK greater or equal V BBK times VKK. That's a special instance of this general inequality over here. It appears in Minkowski's paper. Now, I told you that many of these objects have geometric interpretation, so let me write the geometric interpretation under it. This VBKK is nothing else than the surface area of K up to some constant. So there's some constant that depends only on dimension. I don't remember what it is off the top of my head. 1/6 or something, or 1/3. So this is the surface area of K. This guy over here is the mean width. Okay. And this guy over here is the volume. So this is an inequality between 3 very natural geometric functions of convex bodies, right? Surface area, mean width, and volume.
What does mean width mean?
So I take my convex body here, let's take it here. So fix the direction, let's say that one. So now let's take 2 hyperplanes with that normal direction. And this is the width. That's the width in that direction, and then average it over all the direction. So it's just the average width. So how should you think about this inequality? So this inequality is kind of reminiscent of the isoperimetric inequality, right? So the isoperimetric inequality says basically that the surface area cubed is lower bounded by the volume times a constant. Right? But here we have a quadratic inequality, not a cubic inequality. So how should we think about it? So suppose we take a convex body, let's say, let's look at all convex bodies of volume 1. Then this has been made 1. And I look at all convex bodies of volume 1 and mean width, let's say A. Let's just call it A. And now I want to minimize the surface area. So the question is, which bodies minimize the surface area if I fix the volume and the mean width? Well, here we have an inequality for the surface area. The surface area squared is lower bounded by the product of these two guys. So if this inequality equates equality, right, that means that among all bodies where I fix the right-hand side, right, the left-hand side is minimized. So which bodies minimize? Well, one choice is obvious, because if I choose K to be the Euclidean ball, then obviously I have equality in this inequality. Right? So clearly the ball, if I fix, let's say, the volume to be 1, and I fix the mean width to be the mean width of a ball of volume 1, right? Then the surface area is minimized by the ball among all of those bodies. But now the question is, if I pick a different mean width, I can no longer be a ball, right? So if I fix the volume to be 1 and I take the mean width to be 1,000,000, right? So that's larger than the mean width of a ball, right? And now I ask among those bodies, which ones minimize surface area? Well, it can't be a ball anymore because I forced the body to be wider than a ball of mean width 1. And then the question becomes, okay, what is the most efficient way to minimize surface area if I've also forced the bodies to be wide? So I don't know, I often ask audiences to guess what would be the right answer. And usually the answer I get is it should be an ellipse. People usually guess if I want to make a ball, it's an isoperimetric theorem, should be minimized by something kind of round, right? So probably it's an ellipse. And it turns out to be very much not the case. So the bodies that minimize these guys look like this. So start with a ball and take a point outside the ball, and I'll take the convex hull of the ball. And now you get this object over here. You see it's like a ball with a party hat, right? Like a hat on it. And I can do it again. So for example, I put another hat over here. Doesn't really matter. Actually, I can put as many hats as I want on this ball. And it turns out that all of these bodies that look like this, they're called cap bodies. They appear in Minkowski's paper. All of these objects over here are actually equality cases of these inequalities. So what this means is that if I fix the volume to be 1 and I fix the mean width to be, let's say, 100, right? The most efficient way of doing it is basically pulling a sharp point out of the body. That's the most efficient way of getting the body to be wide, while still minimizing. And if you think about it for a moment, it's a very surprising kind of object because it looks nothing like anything you ever see when you study isoperimetric inequalities. Usually when you study isoperimetric inequalities, what do you get? Right? You get body, minimizers are smooth, they're kind of round, right? They have constant curvature, they're unique, right? And here this is completely and manifestly false, right? So these bodies are not smooth because they have these sharp corners. They're highly non-unique. So if I fix the volume to be 1 and the mean width to be 100, there's uncountably many of these bodies because there's many different ways of achieving those two constants by putting these caps, for example, in different locations, taking a different number of caps. So it's completely non-unique. It's completely non-smooth. So from the point of view of isoperimetric inequality, these are very, very odd objects. But this turns out to be, so these are all minimizers. And now the next question you would ask is, are these the only minimizers? In the Minkowski's paper, these were conjectured to be the only minimizers of this specific example of that inequality. And that was proved 40 years later by Bohl. These are the only minimizers of that particular example. And for the longest time, that was basically the only resultant. So Bohl uses some geometric construction to prove this, which is completely useless for addressing the general problem. This turns out to use this special case has a very special feature that allows that is simply false for general equality cases of these inequalities, which allows you to have some kind of geometric argument. But it's not useful even as a starting point. So good. Are there any questions? So you already see that there's kind of interesting structures coming up. There's kind of unexpected minimizers. And now if you think about this as a kind of far-reaching generalization of the isoperimetric inequality, where you have 3 very general geometric functions of convex bodies, and now you ask, okay, if I fix those 2 numbers, which one minimizes the left-hand side? Now you can imagine in complete generality, you get even more complicated objects coming out than in this very simple picture that I drew. So
could you explain why those are equality?
No, not now, but I will try to explain a little bit later. I will try to explain a little bit more later what some of the equality cases.
Is the isoperimetric inequality a special case of this?
So there, yes, you can, because you see these inequalities only vary 2 of the bodies, but I could of course put together many different cases of these inequalities, and it's known there's standard kind of algebra tricks and how to do it. In the 3-dimensional case, for example, it's on the side, you have 2 basic inequalities, which is that one, right? VBKK, VBK, VKK. That's one of the non-trivial inequalities. And the other one is VBK squared greater or equal to VBKK, VBBB. This one says that the mean width is lower bounded by the surface area, This one says that the surface area is lower bounded by the mean width times the volume. And if you combine these two inequalities together, you get the isoperimetric. But it turns out, for example, that this inequality over here, the second one, doesn't have any non-trivial equality cases. The ball is the only problem. And this inequality over here has these very strange equality cases. So if you just look at these inequalities, you don't see any difference. So there's some structure lying underneath, and it's not entirely clear what is making them. It will become a little bit more clear. Any more questions?
Can you explain why it is the surface area? I cannot see it if it is a very small ball, but for a large ball.
I think, what is the question?
Why does this give the surface area? I would think you need a small ball. It's not okay.
But it's a, you see, it's a derivative. So the surface area is, what is it? It's it's ddt of the volume of K plus T times the Euclidean ball at T equals 0. So now just write out, right? So what is the volume of K plus T times B? Yeah, you just plug it into this formula over here. And you see that the surface area is just the first order term in the expansion, right? So that's where. These are elementary facts that I kind of sweeping under the rug. Yeah, it's not a deep fact that this gives you a surface. Any more questions? So, for a long time, right? So these questions appear in the very earliest papers. And for a long time, there was zero progress on these type of problems. And you can find in the old papers from 1930s and 40s, and also in textbooks, you can find kind of statements that people didn't really believe there was a meaningful answer to this question. Right? So the question is, can we characterize geometrically when you have equality? And people believe this was kind of a hopeless question. So, for example, in the book of Burakos Al-Galar, there's a famous book on geometric inequalities. There's an entire section on this problem. And he writes the equality cases of this inequality have not been characterized, probably because there are too many. So it's not quite clear what even to expect. What made a huge difference is that in 1985, Schneider published conjectures. So Schneider published some kind of detailed conjectures on what the equality cases might be. And as you can already tell from just the short story, it shouldn't be obvious how to even characterize these equality cases. But Schneider had a beautiful insight about how, what should be the structure of these equality cases. And after Schneider's paper of these conjectures, there was a little bit more work on this, but not a lot more progress. Just some very special cases, there was progress. So as you will see, Schneider's conjectures turn out not to be complete. There are even more equality cases than Schneider conjectured. But without those conjectures, we would be nowhere. We wouldn't even know where to look for the equality. So a few years ago with Yair Shenfeld, what we managed to do, we managed to make significant new progress in this direction. And before I discuss what we did, I want to explain a little bit what, why is it hard, let's say? What's the problem? Why can't we characterize these? In most inequalities that you encounter, the equality cases are not really difficult to characterize, right? So, what is the problem here? So, what turns out to be the problem is that, right? How do you normally prove equality case and inequalities? I have proved an inequality, now I want to prove its equality cases. What do I do? Well, inside the proof, you just go into the proof. Inside the proof of the inequality, you make step one, you make one inequality. Step two, you make another inequality, right? And you go until you've proved the end result. And then if you want to know the equality cases of your end result, you go back in the proof, and every time when you made inequality, you check what happens when it's equality. You put everything together, you get the equality case, right? So that's normally how you find the equality. The problem with the Alexandrov-Fenchel inequality is that this inequality is actually not proved for general convex bodies. The inequality is proved inside the proofs. What you do is you assume that these bodies are very smooth. Okay, so for example, Alexandrov had two proofs of these inequalities. One proof of the inequality assumed that all of the bodies were smooth and had positive curvature. And the other proof of the inequality used polytopes, but not arbitrary polytopes. They used polytopes that were combinatorially equivalent. and which is just a discrete version of smoothness, if you will. And it turns out that in those cases where, in those cases that are used inside the proofs, there are never any non-trivial equalities. All the equality cases are trivial. So just to be clear, what trivial means here, there's two obvious equality cases. One of them is if K is equal to L, obviously you have equality, right? And the second one is if you take any of these bodies and you translate them, right? Because volume is translation invariant, these mixed volumes are also translation invariant, right? So if you take any of these bodies, you translate them or you scale them. So volume is n homogeneous under scaling, which means that these mixed volumes are also homogeneous. So these are homogeneous inequality. Okay? So if L equals K up to translation and scaling, we call those the trivial equality. Right? And the interesting ones are the ones that are not trivial. But it turns out that in order to prove these theorems, what you do is you first assume some conditions under which there are only trivial equality cases. And then you prove the inequality under those conditions. And then at the end, you take a limit, right? So because you can approximate any body by a smooth body, you take a limit in the end and the inequality still holds. But what happens is that all of these interesting equality cases, you see these equality cases are not smooth, they have these corners. And all of the interesting equality cases happen in the limit. They appear only in the limit. They never appear inside the. In fact, it's even worse than that. It turns out that the way these inequalities are proved, I don't want to go into it right now, but the way these inequalities are proved, the fact that there are no non-trivial equality cases is actually the main point of the proof. Right? So what Alexandrov does, following a method of Hilbert, is he starts by proving there are no non-trivial equality cases. And then he can use a kind of homotopy argument to prove the inequality. Right? You start from some case you know, and you have some continuity argument. And as long as you can have no non-trivial equality cases, then basically what happens is that the sign of the inequality can't flip. Right? So that's the way the argument works. So the fact that there are no non-trivial equality cases is actually the main point of the proof of these inequalities. And we're trying to characterize the non-trivial equality. So what happens in these inequalities is that, okay, so inside the proof, there are no non-trivial equality cases, and in the non-trivial ones happen in the limit. The problem is that if you take the limit inside the proof, you go in the proof and look what happens if you take the limits to non-smooth bodies, everything that lives in the proof becomes singular. Right? All the objects in the proof blow up, they become singular. And then we don't know what happens to it. Right? So we get stuck. And in a sense, it has to be that way. So the structure of these equality cases is really encoded in the structure of the singularities of the objects of the pyramid. And so the real difficulty of these proofs is to kind of tame these singularities, right? To find a way to understand how these singularities arise and what to do. So we have to understand these singularities. And it turns out that these singularities, they actually, they are problems for us in completely orthogonal direction. So there's really two ways in which these singularities hurt us. There's analytic singularity, and there's combinatorial singularity. So the analytic singularities, they arise. Why do they arise? So, you know, the surface of a non-smooth convex body can be extremely nasty. Let me give you an example. So here I took a ball, right? And I put two caps on it, right? I have an equality case. But in principle, I can put as many caps as I want. Okay? So in particular, I can put on a countable number of caps. So let me make for you a construction of a really obnoxious body. Okay? Take a sphere. Now on the surface of the sphere, I can take an Apollonian circle pattern, right? Alex has disappeared. Huh? I can draw it. So take a dense packing of spheres, right? Just keep drawing spherical caps on the surface, right? And just keep filling in the holes between the balls with more, right? You can do this as many times as you want. And you get this kind of fractal pattern of spherical caps lying on the surface. Now, anytime that I have a bunch of spherical caps that are disjoint except on their boundary, I can take the center of the cap and I can lift it to create, right, to create a cap like this, right? So I can take a cone that exactly touches the surface of the sphere tangentially at the boundary of the spherical. So if I do this, what I get is I get a convex body, a cap body, in fact, in the equality case of this inequality, whose surface has a kind of fractal pattern of spikes sticking out of it. Now, this is a really nasty object. This is a highly non-smooth object. And if you look into the proof of these inequalities, so these things, the way they show up in the proof, think of them as being quadratic forms of these first two bodies, right? So for example, if you're dealing with polytopes, these will be matrices. If you deal with smooth bodies, these will be elliptic operators on the sphere. And if you now take the limit as they become non-smooth, you get some extremely singular looking elliptic operators that live on kind of fractal structures that could show up on the surface of the sphere. And we don't know how to analyze or even define properly. And now we know how to analyze them, how to define them, but we don't really know how to analyze. Right? So we get issues of singular elliptic operators, geometric measure theory, etc. We get these kind of problems that the objects that appear in the proof, they become extremely singular, they are highly irregular, and we don't have a good way of analyzing these. Then we also have combinatorial problems. So suppose now that all of these bodies were polytopes. Suppose all of them are polytopes. Now these are just matrices, right? There's nothing fancy going on. They're just matrices. But we have all of these different convex bodies, and each of these different convex bodies, they have a different boundary structure, right? So the boundaries of a polytope, they are described by their normal fan, right? By their normal cones. And when I have n minus 2, for example, C1, C2 until Cn minus 2, they all have different normal cones that interact with each other in a kind of complicated combinatorial way. And these combinatorial interactions are also encoding, I will write down the theorem in a moment that will make this more clear, are also encoding these equality cases. So, so we have the interactions between the normal fans of these different bodies that are kind of conspiring to give us equality cases, and one has to understand how to analyze the combinatorial structure. So these are really two very distinct kind of problems that we end up having when we try to deal with these singularities that arise in it. So the current status, roughly speaking, is that we have understood how to handle these kind of singularities, and we have understood how to handle these kind of singularities, but we don't know how to put them together. So we can handle these analytic singularities in special cases of the problem where there are no combinatorial singularities. Basically, that's the case where all of the bodies C1 through Cn minus 2 are the same. Okay, so that case we can handle. In that case, we don't have a combinatorial problem, but we can handle these kind of analytic problems. And we can handle these combinatorial singularities in the case of polytopes, where everything is a matrix and we do not get analytic problems. So, but we don't know how to put these together, and the general problem is still. So it took me half an hour, more than half an hour to get there, but let me write down something resembling it. This is Shenfeld and myself. So in this talk, I want to focus mostly on this combinatorial side. We have a side, we have results there too, but let's focus on the combinatorial side. So the theorem is a complete solution to the problem when C1 to Cn minus 2 are polytopes, arbitrary polytopes, convex. So here we have only the combinatorial problems, and we do not have the analytic problems that I just described. So
So K and L don't need to be.
I beg your pardon?
K and L are not supposed to be polytopes.
K and L do not have to be polytopes. However, this is not really an issue, because it turns out that if C1 to Cn minus 2, this shouldn't be obvious, but if C1 to Cn minus 2 are polytopes, and you start with any K and L that you have equality, I can always modify K and L to become polytopes, so you still have equality. So in the proof, this actually doesn't turn out to be. It shouldn't be obvious. But it's really the properties of these bodies that are not changing, which are the difficulties. So I left myself nice room over here on this board to write the statement of the theorem. But remember, the conjecture of Burago and Zalgaler that there are many equality cases is in fact true. And it took us in the paper maybe like 10 pages to write out explain all of the different equality cases. So let me just kind of, I'll write it like that. Let me just kind of hand wave what are the phenomena. So there are three mechanisms that cause equality. So the first one is translation and scaling. This one is the trivial. Right? If I translate or scale any of the bodies, right, I don't change the equality cases. That's the trivial equality. The second mechanism comes from the relative positions of the normal cones of the boundaries of these reference ones. So if I take a fixed direction u in the sphere, and now I look for each of the bodies C1 to Cn minus 2 at the cone of normal directions, right? That contains u. So they can be cones, but they can have all sorts of different orientations. And the relative positions of those cones, they describe this combinatorial structure that is causing the equality cases too. And there's a third mechanism which was not conjectured by Schneider, so these can be even more equality cases, which are the relative positions of the spaces in which the bodies themselves lie, of the affine holes of C1, of Cn minus. Right? So these, if you see, if I have convex bodies in Rn, they don't have to be n-dimensional. I can take a flat pancake. That's still a convex body in Rn. Now, such a body has volume 0, but the mixed volumes of these bodies is not necessarily 0. Right? Because if I take a flat pancake in this direction and I take a flat pancake in that direction and I add them up, right? I get a cube, I get something with positive volume. So these bodies C1 to Cn minus 2 don't have to be full dimension. They could be lower dimensional. And if they live in kind of subspaces with bad orientation, then you can get even more equality cases that are caused by. So these are three different mechanisms. And these three different mechanisms can appear in superposition with each other. So they give rise to different kinds of equality cases that superimpose to give even more equality cases. And it has to be handled in.
I don't really understand what you mean by the second being a mechanism. What do you mean by that?
So I think the best thing I should do is just show you a kind of example rather than write down the definition. So I'm going to give an example of an equality case.
So you're doing dimension 3 already?
This is dimension n. No, here we're in
No,
dimension.
What do you see in dimension 3?
All three of them.
Okay.
In dimension,
In dimension 2, there are no non-trivial equalities. This was known to Minkowski.
Was Alexandra's proof very different from Minkowski's?
I beg your pardon?
Was Alexandra's proof very different from Minkowski's?
Yes. There's a reason why Minkowski only proved in 3 dimensions. His proof doesn't work in either, though it's fundamentally different. However, so Minkowski, he first proved the cubic inequality, the isoperimetric inequality, and then he polarized. So what he did is he took an isoperimetric inequality, which is a cubic inequality, and then he plugged in linear combinations like this. And if you let some of the lambdas go to infinity, you can get these quadratic inequalities. So it turns out if you do that, you can get the inequality in any dimension, but only if all of the C1 to Cn minus 2s are the same body. And that in that case, we know the general equality cases on this side. You can resolve this side. But if you allow yourself to have n minus 2 different reference bodies, that no longer work. And it's a fundamental difference between, basically Minkowski's original inequality was about the second variation of volume, right? You take 2 derivatives of volume. But the Alexandrov-Fenchel inequality is about the nth derivative of volume. So it's a much more delicate. However, what happened was that in a few years after Minkowski published his paper, Hilbert published a new proof of Minkowski's inequality. And the new proof works completely differently than Minkowski's proof. It uses spectral theory. And Alexandrov's proof of the Alexandrov-Fenchel inequality is based on Hilbert's proof of the Minkowski quadratic inequality. So there's a long story about this that I will tell you some other. So Let's write down again in 3 dimensions because it's easiest to visualize it. Let's write down inequality. So what we do is we start with, let's start by making the all unit cube. And this one too. This is also a unit cube. Okay, this is obviously an equality case because now K equals L equals C, right? Up to translation. And now my claim is that this remains an equality, if this remains an equality case. So remember, C here is fixed and K and L vary. What I claim is I can take these bodies K and L and start cutting off their corners and nothing bad will happen. Okay, so for example, I can take this guy and slice off one of its corners. And I can take this guy and slice off some corners. Maybe that one. Slice that one off. Slice this guy off. Doesn't really matter which corners. I can slice some of the same corners off, but to different height if you want. There we go. So you see, here I have this guy remains a cube. And these guys originally were cubes, and I sliced off some of their corners, and I claim that this is still an equality. So why is this true? So I'm trying to explain to you this mechanism too. So what I'm saying here is that it's the relative position of the normal cones of C1 to Cn minus 2, but here there's only one body C. So let's think about the normal cones of this body, right? So it's a cube, right? So for example, suppose I look at the normal cones of the facets of the n minus 2 of the 2-dimensional face, right? So they go like that and like that. So you see, in those directions, these two bodies are always the same, right? Because if I fix the direction of a facet and I look at the plane that touches the two bodies, it's the same plane in all facet directions. And another normal cone I can look at is the normal cone of the edges. So pick an edge. Here's an edge. So what is this normal cone? Here it's the normal cone of this edge, right? These are all the normal vectors to that edge. So let's pick some vector that's normal to an edge. And look over here. Well, here I have this edge. Here, the edge is still in the same place, right? Because cutting off this corner didn't change where the edge is. So in any normal direction of an edge of this body C, these two bodies have the same supporting height. But if I look at the normal directions of a corner, right? So if I look at the normal directions of a corner, right, I get this 3-dimensional normal cone. Now these two bodies can be different, right? Because for example, if you look at this corner, here I didn't cut that corner, right? So here, if I take the hyperplane, right, with that normal direction normal to this body, it's further out than it is over here where I cut off the corner. So these two bodies have the property that they have the same supporting hyperplane in every direction that's normal to a 2-dimensional face or to a 1-dimensional face, but they can differ in those directions which are normal to a corner. That's the kind of mechanism you should have in mind. Explains this picture over here, right? Because here I have this body and the other body C. Sorry, this was the body C and K, and this was L. So you see, if I pick a normal direction to a corner, this body and that body can be different, right? Because this corner is much further out than this guy, which doesn't have a spike. But if I pick any direction that's not normal to a corner, these two bodies are the same because they are made from the same underlying ball. Does that make sense? Now, what happens in general is that in general, I have n minus 2 bodies. So what happens in general is that those n minus 2 bodies collectively determine a set of directions which are good directions and bad directions. And it depends on the relative positions of the normal cone. So I pick a direction u, and I look at the normal cones of each of these bodies that contain a direction u. And the relative positions of those normal cones that determine whether direction is good or bad. And then the statement is that we get equality as long as the two bodies have the same supporting hyperplanes in the good direction. But in the bad directions, they can be. So that's the idea. But in general, it's not each individual body that's determining whether a direction is good. It's the relative positions of the cones, which is this combinatorial structure. So I could write a formal definition, but I hope that the picture gives you some kind of idea of what it is. Now, these equality cases over here, they're far more complicated and they're very strange. So I'm not actually going to talk about them.
So in the second part, is your theorem saying like basically what you said, or is it much more detailed? Like in this case?
It's saying exactly what I said with proper definition of what it means to be good in them.
So if I give you, 17 bodies, it's
Yes.
like difficult problem to determine what's the good direction. Computationally difficult.
Perhaps. It's no more difficult in determining the direction of the normal cones. So if you can give me the normal fans, right? If you can give me the subspaces in which the normal fans live, then it's an easy. That's actually not a difficult problem. This guy, it turns out to be computationally difficult. That's a theorem of Igor Pak and Chan, who proved that these equality cases, number 3, can be computationally difficult to check. But these equality cases are always easy. They're not problematic. Yes.
So sorry, so you described the mechanisms, but is that theorem of the type that you also classify the starting cases and you say every other case can be obtained through those mechanisms? Or is it of the type that if you have equality case, then you can use the mechanisms to get more?
The theorem is completely explicit, right? So it says that if you give me K, L, C1 to Cn minus 2, all of them are polytopes. K and L don't even have to be polytope. And you have equality, then you have equality if and only if. Some, so there is a translation, a scaling, such that in all of the good directions, the support functions agree. That's just saying they have the same supporting hyperplanes of K and L, except if you have these guys, which is more complicated. But again, there's an explicit restriction. Good. So I just want to say a very quick word about the proof. So I said the problem is singularities, right? So if you look in the proof, right? For example, if I take the key point about these matrices is they have different combinatorial structure. If all of the matrices were to have the same combinatorial structure, right? For example, if I also slice off the corners of this guy, I slice off the corners, but all the same, all 3 of them the same way, right? I don't have any non-trivial equality. So what happens is that there are some matrices that appear in the proof, and if you make if you go to the non-smooth case where the combinatorial structure is no longer the same, the entries of these matrices blow up and you get a mess. Okay? So the main idea of the proof is a kind of resolution of singularities. So in principle, what we would like to do, right? So let's say we're in any dimension n and we want to characterize the equality case. So we start with an equality case. What we really like to do is argue by induction, right? So we'd like to say, okay, if I have equality in dimension n, then maybe if I take some projection of these bodies onto an n-1 dimensional plane, I get equalities in dimension n-1. And if I can do that in every direction, then I can glue together that information and get information about the equality case in dimension n. The problem is that that's simply not true. Because you see, I mean, if I look at this example and I pick a bad direction, right, and I project onto some 2-dimensional plane, right, I can certainly pick a 2-dimensional plane so that the projections of these 3 bodies don't give me an equality case. They don't, because in 2 dimensions, you only have trivial equality cases. But it's clear you can pick some projections where this becomes a square, and these 2 guys become like squares with some corner cut off, right? And that's not an equality case in dimension 2. So it's simply not true. It's simply not true that the equality cases here are preserved by projection, by induction of the dimension. But what we know is that we have a lot of degrees of freedom here. Maybe that's along the lines of your question. We have a lot of degrees of freedom here because we have good directions and bad directions. And in the bad directions, these bodies can be anything, right? They don't have to be the same in those directions. They only have to be the same in the good direction. So what we could do is we could take, for example, this equality case and fix some bad direction, right? Which in this case is a normal direction of a corner. And we can start changing the bodies in those bad directions. And that wouldn't change the equality cases because the equality cases only require us to be fixed in the good direction. So the kind of engine behind the proof is a theorem that says that given any equality case, there's always a way of perturbing these bodies only in the bad directions in such a way that then after I perturb them, if I project, I get an equality case in lower dimension. And basically what that theorem does is it kind of eliminates the singularities that appear inside the proof. So there is a way of eliminating the singularities that appear inside the proof by only moving these bodies in the bad directions. So that after I've done that, I can reason by induction on the dimension. And surprisingly, this is basically, it has very little to do with geometry. The proof of that statement is really a linear algebra argument. And it's not an argument that requires specifically to work with convex geometry. And that makes that idea presumably useful also in other situations. And we don't know yet how far that. I'll get back to this. All right. So I hope I gave you some flavor. Now, I want to change gears and tell you something about something that many people in this room know very well. So these inequalities have deep connections to law concavity. So that the sequence of numbers, let's say non-negative numbers, positive numbers, is law concave if ni squared is greater or equal than ni plus 1. And there are many sequences in combinatorics that turn out to be law concave. And in many cases, these were long-standing conjectures, and many of them have been recently solved. But one of the oldest ideas in this area is due to Stanley. So Stanley investigated a question about partially ordered sets. It was one of the first inequalities of these kinds. So let's take a partially ordered set. We take a partially ordered set. And I have here one distinguished element that I fixed. And I'm going to call Ni is the number of linear extensions of P such that X, this special element X, has rank I. So if I have a partial order, I can always add more relations to that order to make it a total order. That's called a linear extension. And given any partial ordered set, we can ask, can we count the number of possible ways that I can augment the partial order to become a total order? That's counting the number of linear extensions. But here I have one element X that I fixed, right? So I'm asking here, what is the number of ways of making this partial order a total order so that this X is rank I in the total order? So there was an old conjecture from the 1970s of Chung, Fishburne, and Graham, which said that this sequence should be log concave. Right? So in particular, it's also unimodal, right? If I increase I, first the number of linear extensions should go up and then it should go down. I should not be able to get some picture like this for the number of linear extensions. So, you know, people try to prove this using combinatorial means, but it doesn't seem to be possible. But it was proved by Stanley as follows. Ni is log concave. How did he do it? Well, here is his proof. Given a partially ordered set, you can cook up two polytopes whose definition depends on the partially ordered set. Very simple construction, not something deep. So you take two kind of order polytopes of P. And then Stanley realized that you can then compute Ni, there's simply a formula, Ni equals n minus 1 factorial times the mixed volume of these two polytopes. This one you take I minus 1 times, this one you take n minus 1. So these are n minus 1 dimensional polytopes in this example. You have n minus 1 bodies. So it's once you have the clever idea of doing this, it's elementary. And as soon as you have this, then the conclusion follows immediately from the Alexandrov-Fenchel Inequality. End of. So if you think for a moment, you ask yourself, well, we have a characterization of equality cases of the Alexandrov-Fenchel Inequality. What does it mean? right? So what does it mean to have equality? Equality in a log concave sequence just means that ni squared equals to ni plus 1 and ni minus 1. That's nothing else than saying that we have a geometric progression in the sequence n. Means that, right? That means that ni is some constant times ni minus 1, and ni plus 1 is the same constant times ni. So the question about equality cases in the Alexandrov-Fenchel inequality is equivalent in a sense to, or in these kind of constructions, to the question about whether we can understand the geometric progressions that arise in log concave sequence. And in particular, you could ask, okay, here we have a specific example. What happens if we apply this kind of technology, right, to these kind of questions? And it turns out that, in fact, we can do this and we can get a complete picture of what these geometric progressions look like. So in this example, for example, what can happen typically, right, so these log concave sequences, they look something like this. So they can be 0 at the beginning and at the end, and they can be flat here on top. But it turns out in this particular example of Stanley, you could never have a non-trivial geometric progression. So you cannot have that ni equals twice ni minus 1 and ni plus 1 is twice ni. You can only have flat geometric progression. That in itself is not an obvious statement, right? It means that the kinds of log concave sequences that you can get in these kind of problems are not all log concave sequences, right? They're highly constrained. They have shape constraints on, which is not something that you can see just by looking at this. But what is more is that if we apply this technology, what we can do is we can compute exactly where these sequences are. So it turns out, right? So there is 4 points here. The point where you're 0, right? That's a geometric progression of the point where you're maximum, where you start the maximum, the point where you end the maximum, and the point where you 0 at the end. Now we can explicitly compute these guys. So this is, for example, this point over here is just the number of elements in the partially ordered set that's less than x. This is the number of elements in the partially ordered set that's more than x. And we can compute these points too. I'm only writing them down so you see that we have explicit, very simple explicit formulas for these. See, they're very simple explicit formulas. If I give you a partially ordered set, you can compute these numbers. That's kind of remarkable that we have these, right? We have these kind of log concave sequences, which in general are kind of very difficult to compute. But if they have flat parts, we can explain where these flat parts are, right? And we can exactly locate them in the sequence. And in a sense, if you look at this picture, you don't see it, but remember we had these wonderful bubbles, these strange, bizarre soap bubbles of Minkowski that have these corners sticking out of them. And this is the same picture, right? This is a kind of combinatorial version of what's going on over here. These weird bubbles over here are exactly the things that cause you to get geometric progressions in log concave sequence. And it's kind of I don't know, I find this kind of a fascinating connection between two very different looking.
What do those mathematical processes look like?
You can ask me later, but I don't have a very clear answer. I can show it, in examples I can compute it, but if you look at the general picture, there's actually work involved in going from here to here, because you see, this condition over here gives you information about the geometry of these polytopes. And these polytopes are they're order polytopes. They're combinatorially defined in terms of the speed. But it's not immediately obvious how you translate geometric information about these guys to the combinatorial information. And there we actually have to work. So, one has to do some reduction. And in that reduction, it's kind of hard to see exactly, except if you look at a specific example, it's kind of a little bit hard to see what happened to the geometry of the polytope.
But these facts that you're telling us now, this is Stanley classical, this is new that you have in your paper with Shenfeld, this picture over here?
Yes, this is new. Well, as of a few years ago. Yeah, so Stanley proved the inequality. But the fact that we can understand exactly where the geometric progressions are, that's the new.
That's you and Shenfeld.
That's right. And in fact, so I want to emphasize that here, for example, I emphasize you can only have flat progressions. But that's a coincidence. So since this first paper that we published here, we wrote several papers where we checked this in other kinds of inequalities of this kind, these lock-and-cave inequalities. And sometimes, for example, you don't just get flat progressions. It's possible, for example, in one of the other inequalities called the convex inequality, which is a similar inequality about partial ordered sets, you can get either flat progressions or progressions of order 2. So where it's ni equals twice ni minus 1 and ni plus 1 is twice ni, but you can't get progressions of order 3. So you can get, you know, and we can characterize exactly when those happen too, and they can't coexist arbitrarily. They can only happen at the beginning of the sequence, for example. So it's really not obvious what happens with the geometric progressions, and it's really this phenomenon over here that's manifesting itself commonly. So I need to wrap up. I want to make some just kind of general remarks. So in recent years, you know, so Stanley derived his lock and cavity inequality from the Alexandrov-Fenchel inequality, but of course we know that in many cases, in many important problems, there simply isn't a representation of lock and cave sequences by mixed volume. Right? That's kind of a lucky that Stanley had this. But what is clear now is that there are many situations where Alexandrov-Fenchel type inequalities happen in other areas of mathematics. It was already known in the 1970s, they happen in algebraic geometry. They're called Chovansky-Tissier inequalities. And those are inequalities for intersection numbers of line bundles and they, or of divisors. And those are really just Alexandrov-Fenchel inequalities in a more general sense. And nowadays, there's all sorts of combinatorial Hodge theories, there's Lorentzian polynomials. Okay, I mean, this is the topic that many of you are familiar with. And all of those inequalities are really Alexandrov-Fenchel type inequalities in disguise. Right? And somehow, you know, my interpretation, which is of course very one-sided, but my interpretation of this whole development is that, you know, even though most interesting problems cannot be expressed in terms of mixed volumes, right? So cannot be reduced to the Alexandrov-Fenchel inequality, one can take the proof of the Alexandrov-Fenchel inequality and import this and prove it directly in all sorts of different situations. So one can prove Alexandrov-Fenchel inequalities directly in many combinatorial problems and many other problems in mathematics. And at some level, you know, what it says is that Alexandrov-Fenchel inequality really doesn't have much to do with convex geometry. It's a more universal kind of object that we see appearing in many different places. So it's a kind of universal structure. It arises from algebraic structure, not really from the specifics of convex geometry. So if you view it this way, then one can ask, you know, these kind of phenomena we see here that are establishing these geometric progressions, are they also universal, right? Or are they specific to the case of convex geometry? And I believe that these mechanisms should also be very universal. This is something that in most, not all, but most cases where one can prove Alexandrov-Fenchel type inequalities, one should also have the same kind of equality conditions that are showing up. And I think it's an interesting challenge to prove that, really in any other situation. In a sense, we see part of the proof of this is very linear algebraic. So much of the proof of this theorem really doesn't rely very much on convexity to begin. So it seems very plausible that there is something universal here too, and that one should have the same kind of characterizations in other situations. But largely at this moment, it's conjectural. There is some progress in algebraic geometry where, let's say, 1.5 of this theorem has been ported to the intersection numbers of divisors by Hu and Xia. And in many other situations, we simply don't know. So I think this is an interesting direction, and I would be happy to discuss it. Anybody who's interested. So thank you.
Questions?
At the beginning, you said when the combinatorial case was as good as smooth, but I didn't understand what it was.
The combinatorial case that's considered by Alexandrov is the case where you take all of the bodies to be polytope and their normal fans are equal. So they have exactly the same normal fans. And not only equal, but simplicial. So this is really you could think of it, if you want to think of it in terms of toric geometry, right? That's the case where you have a non-singular toric variety, and all of the divisors are ample. So that's a very smooth situation, right? So that's and it's analogous. The analogy with smoothness is that The continuous proof of Alexandrov uses smooth bodies with strictly positive curvature. And the fact that the curvature is strictly positive is really equivalent to the ampleness of the, does that make sense? So, but those are really two, I think of those two phenomena as being the same phenomenon, just in two different states. Right? Smooth bodies with strictly positive curvature and right, polytopes with the same normal fan, this is really the same. Because it means that the support functions are going to be convex on the boundaries of it, right, on the raising. Strictly convex. Yes.
What data describe the relative positions of the normal cones?
So, I mean, it's. So for polytopes, we usually think about it as in terms of the faces, but that's just a dual state. I write it down and you can just dualize it. So a direction U is good if for all K and for all I1 to IK between 1 and n minus 2, the dimension of the face of CI1 with normal direction U plus CIK with normal direction U is at least K. So if you dualize this is saying that the dimension of the intersections of the normal cones of these bodies that contain U is at most n minus 1 minus K or something like that, or n minus K. And this has to be true for every K and for every choice of bodies I want to write. So yeah, it's a dimensional condition. It's not a numerical condition. It's a dimensional condition. It just says that the normal cones, they cannot, right? They cannot contain, right? You cannot have K of these bodies whose normal cones contain a very large. That's basically. So it's a little bit fussy, you know. I mean, I could have written this all down over here, but it wouldn't have really enlightened you. It's a little bit fussy, but it's just about dimension. It has nothing to do with there's no numerical conditions here, which is why it's easy computation. It's just a statement about that.
Okay, we got already many questions during the talk, so maybe we thank Ramon again.